Alright, time for another draftphysics.com video presentation. Debatephysics also.com. But we don't have debate in any kind of consistent or real form of back and forth interaction or any of the things necessary to really call it a debate. So, not debating much yet. Okay, so this video is going to be on Einstein. It's going to be my version 1.0. Just kind of slopped together, but at first I'll just point out that I do have videos on the website where I am addressing specific comments by people, or videos where they say they have a piece of evidence or some other mush, and I make an effort to explain and defend what I think is the more reasonable interpretation, the more reasonable categorization of meaning, and whether or not there's something to pay attention to. Anyway, so there's a bunch of that on kinetic energy mostly for this last week and such. So on to the more important subject, Einstein, which means I have to do this and this. Alright, that should do it. So it's just a bunch of keywords, really. So I've been reading Einstein's letters over the last couple of months, pieces of it here and there, an Einstein book, called Einstein, and none of it's very chronological, and so it's kind of hard to get exactly how he was thinking or what he was thinking at any particular time, and all of that changes for any human being. They have subjects that are more interesting for a decade and then something else. So there's so many things to note. I guess the most important, most obvious thing about Einstein is that all of his fame is from when he was, 20 years old. And, the 5 papers, blah, blah, blah. And after that, it was just defending those arguments, some of them, and still pursuing better answers, more complete answers. I mean, once you establish, it's sort of the wave-particle argument. He was on the particle side in that discussion. He was on the Newtonian corpuscle side, and there was still a substantial amount of weight, pushing against that argument. So he did spend a lot of time. Shortly, a couple of years before he died, he said, I've been studying photons for 50 years, and I haven't improved my understanding one iota, kind of a statement. He hadn't improved his understanding. And this was really one of the key ideas, is how, what forces are. In complete contradiction to that, you could argue. So I guess I'll go to the other keywords, frankly. This will be more important. His other papers, Brownian motion, which was just this idea that there's inherent in the universe, apparently, an awful lot of movement on the small scale. Everything's moving so much that you can't see things in a microscope because everything's moving too much. And that it's not just related to heat, that it seems, even more randomized, even more elemental situation. And so that sort of indicated that there was something, this action underneath all the action. And the photoelectric effect sort of relates back to Faraday and fundamental arguments about the who moves into what and what moves into who, and you start getting into arguments about redshift of light and arguments about why light doesn't increase in speed or decrease in speed. And so that was like a fundamental argument. And then he also did stuff on radiation, in terms of that's where the mc squared came from, the E equals mc squared, in the sense that obviously the radioactive body is losing mass as it's ejecting its energy. And clearly, because of how much energy was coming off of something and how little mass it was losing, you could make the argument that it has an insane amount of energy in it. The capacity of a clump of uranium to produce energy, almost like a sun, for a very long time. obviously indicated that there was an awful lot of energy in just any little piece of matter. But that's the real problem, is the jumping to a bigger conclusion than the evidence really points to, in terms of maybe recognizing that it's not the mass that actually has the energy, it's the composition of the mass, that is the formation of atoms, and that the atoms have energy, and the energy caught in creating the arrangement of the electrons and protons, the charges interacting with each other, is the elemental energy, and the bits themselves don't have any. So lots of subjects. So throughout his life, he was. The real problem with Einstein is the reason why Einstein is just like a one-hit wonder. Like, okay, he did all this brilliant stuff when he was young, and then nothing else, is because the subject changed so dramatically, and he was outside, not an insider. He became an outsider relatively quickly. Because he was still defending basically a corpuscular theory. He was against the spooky action stuff. And, the obvious, what I see as an obvious contradiction in his thinking is the capacity that he could so aggressively defend his relativity theories when at the same time he's arguing for a materialistic universe. So he's basically, with special relativity, he's destroyed the idea of absolute three-dimensional space. So he's just broken any notion that there could be something sitting in the universe that's not doing anything. It's just sitting there, relative to everything else. It doesn't possess any energy, any motion. And he's turned this motion idea into something that's just relative between objects or something, and somehow the objects themselves don't contain any energy, in a way. Nothing can have any energy if energy is just based on relative motion. Then you don't assign any motion, or you don't assign any change in an object. Anyway, it's a breaking absolute space is a rather bold move, and I'd say a decisively bad move. And so I think that was part of the reason why he couldn't go anywhere, is because he was still defending his old ideas. That I think just were completely incompatible with any notion of a corpuscular force. Force is made out of something, moving distances in time. You just break all of that because you can't really give the force any momentum. You can't give it any energy because your notions of relativity are going to break down, in my opinion. Anyway, so that's just pointing out that's one of the huge contradictions, is he's defending relativity theories that, the first one breaks absolute space. The second one, general relativity, basically tries to say that gravity is the same as throwing a baseball. The forces are the same somehow, and they're not the same. So it's called the equivalency principle, but the equivalency is so superficial. The sameness is so superficial that it again breaks perception of the actual object. So I don't even say that goes all the way to the photon, because once the idea that the photon is quantizable, that is, that you can say it has a specific amount of energy, was a good idea. But the idea that the photon itself was an object, a solid object, a thing, an elemental thing, was a huge mistake, because the photon is really a composite object. It's made of elemental things. It's made of that elemental quanta, that m equals mc squared. That tiny quantizable amount of energy is something a photon contains more than one of. It's not a single thing. It's an event. Photons are events. And so that's another, I would argue, from my reasoning and putting together all the little facts, that was another big mistake. So obviously I'm defending a model of the universe where it is all corpuscular. It's all what the big universe looks like in a small scale. In a sense of its overall look, it's just objects banging into objects, and they bang into each other based on the fact that there's something between them that's doing the banging. So the model is giving you a description of those actual little rocks of momentum that are between objects and causing all of those interactions. But it's all it's all stuff moving through 3 dimensions of space, and you can't break time. So the whole reason the time thing comes up for Einstein is this idea of why time doesn't increase or decrease. That is, if light is bouncing off of something, why doesn't it increase in speed in the direction? If something's moving towards you, the idea is that the common idea is that things bang into something and they gain the extra speed. So if you throw a baseball at a car and the car is moving towards you, the baseball comes back at you at a higher speed than you threw it. If it's rubber and elastic, that's probably a bad example. use like a little kid's ball. It's very elastic, an air-filled ball, and you hit it with a car. You throw it at 30 miles an hour, the car's going 20 miles an hour, the ball leaves at 50 miles an hour. So that idea is what they were looking for in the mechanical universe, and it wasn't there. And so that's what Einstein used as an argument to, the point is that without that mechanism, the whole Michelson-Morley thing, all of the ideas of a drag universe where this stuff really has to be accounted for, it has to move through a real universe of real stuff. And so I would argue in a sense that the relativity theory was a way of evading having to deal with drag, in the sense that once, the relativity theory that deals with time, breaking time, because using time as a dimension, because time just becomes another word for drag, in the sense that you can, if you change how you think the object is, how fast it's moving, in some relative space, in some frame, then you can account for the fact that that's exactly what drag would have been doing if you didn't time dilate it. So if you didn't say it was time dilated, it would have been drag, or ether drag would have done the same thing. So in a way, I think it had something to do with the fact of trying to understand how something could move through space or move through an ether without there being drag. And there wouldn't be drag if you just change how fast something's moving by changing what time it is, if you get my meaning. It's a little bit of a complicated argument. All right, but we'll deal with the photon one first, just because the light clock, the whole imagining thing, it's an interesting subject. Plus, it kind of gets to what I think. Just the fact that they just didn't think about it enough, maybe. And if they had thought longer before publishing and committing, then maybe, they would have had a better answer. So the situation is, you have something. Say if I had a box full of energy, and and the stuff is, I can imagine it bouncing at consistent speeds inside the box. And then I move the box. Then you could say, well, the stuff hitting this side, the box moving this way, is going to increase in speed. And that's a real idea, it happens in thermodynamics that that's how energy increases in a system, is as one piece goes in with a little more energy and it sort of spreads the energy to everything else, the increase. So anyway, so you'd be getting an increase in velocity for the little stuff bouncing around hitting this wall, and then a decrease than the stuff hitting this wall because it's going away. So it's losing its energy as it hits that wall. And the idea would be is if you release something, obviously if you release stuff going this way, it's lost energy. If you release stuff going this way, it's gained energy. So if I poke a hole here and allow something to fly out, it has more energy. If I let it fall out this hole, it's lost energy. And that's sort of what the argument is this is how things would interact in the universe. So it really just goes back to just banging objects into each other. So I could argue that if you could imagine an electron, or something like an electron, whatever, an object in space that wasn't moving, but it was very Newtonian, like it was just another piece of mass, a weight. So it was just a metal ball of a specific weight, and it was the same weight as all the other stuff in the universe. What if, okay, what if we just say that this one, say it banged into this one and it shared its velocity, the two of them stuck together. And so now they're going to say half the speed because it's twice the mass, and this was the only one that had any velocity to start with. And then this one hits it coming this way, and this has a 1 unit of velocity. So this has a half unit of velocity. You could argue that what's going to happen when this interaction takes place is this thing in the middle, because it can share energy with either one of these things, that what you're really going to end up with is this one's going to end up just staying stationary. This one's going to go this way at a full 1 velocity. And this one here, okay, so we have A, B object, and C object. So B goes back to being nothing, not moving, no motion. A ends up going this way at 1 velocity, which it started with. And C ends up going this way. And what have you really done, though, is you've really just taken C and made it go straight through, and you've really just restored A back to what it was doing, going straight through, in the sense that these two objects are indistinguishable. I mean, the A or the B or the C doesn't really matter. They're the same mass, just moving through space. So in a way, you could sort of understand that this transfer wouldn't create any increase in speed. There would be an interaction, but the interaction wouldn't increase something's speed. It would just, all the players would end up being the same speed, a constant speed. So you could have something going an irregular speed, the matter, the electron, all right, but everything else, okay, only goes 1 speed, the speed of light, because every interaction is really just two balls of the same mass, the force. It's just two elements of force hitting each other, all right, and you're getting the Newtonian reaction of just getting back what you put in, and it's as if this one just went right through the other one, and this one just went right through that one. You don't have any change in the actual universe. I mean, the universe doesn't, it's like the interaction didn't even take place. It's like they missed each other. Them missing each other would look exactly the same. The universe would look exactly the same as them hitting each other if you could say this interaction happened without any loss in time. So the universe wouldn't look any different if they completely miss or if they completely hit. So that's one way of understanding how you could have a universe full of a force that is interacting with the other force. Is the fact is that it can't interact in any way that can change anything. So I just say that this little chain of reasoning gives you a reason to understand why I could push my hand into a force, and the force wouldn't leave my hand at some increased speed. It would just do this. And by doing something like that, it would just mean that the force would just collect on my hand. It wouldn't fly off at my hand at some new speed, or that I would actually end up compressing the force, in the sense that the force could be coming at regular rate. The rain could have an inch between each drop coming at me, and I could push into it, and now the rain only has a ½ inch between each drop, or a 1/4 of an inch, or an 1/8 of an inch, depending on how fast I push into it. So I can not only change the frequency, which we see in redshift and blue shift, but more than that, I'm changing the profile in space. I'm compressing an event that takes place over this much distance into an event that takes place over this much distance, which could be argued that that's going to have an effect on things that it hits, in the sense that the faster you hit something, the more regularly you hit it, the more you hit it in sequence with its resonance. So that's another argument I've been making for a long time, is that this whole idea of understanding tipping points, and that atoms would have them, and the idea is that it's like a pendulum swinging. If you want to put energy in, you have to put it in when the pendulum's swinging in the right direction. And if you put the energy in when the pendulum's swinging in the wrong direction, you're taking energy out of the system. So if you want to add energy, you always have to hit it while it's moving away from you, so you can add the energy. And that atoms work the same way, that each atom has its motion, its electrons are in positions, and once you start them wobbling in a direction, you can push them out of the atom, okay, if you're putting the energy in, multiplying the energy by putting it in while the electron's going, while it's oscillating in the right direction. If it's oscillating in the wrong direction, you can't add energy to that electron. And so that's the photoelectric effect. So I'm saying, because they didn't have that model, they weren't thinking of it in those terms. They were just thinking of some absolute amount of energy. They just put the electron at the bottom of a well, and they're saying, how do I bounce it out? How do I bounce it out? How do I bounce it out? And they're not really thinking that what you're really trying to do is cause it to bounce, cause it to oscillate, cause it to vibrate, and take advantage of the fact that that oscillation will have a resonant frequency, and that if you can match your frequency, the frequency of your photon, okay, which is more than one object, if you can match the frequency of your photon to that vibration you've created in the atom, that clearly you're going to be able to add a lot of energy. And if you don't match them, you can understand why, yes, you cause the bouncing, but the bouncing isn't much of a bounce because you keep adding energy at the wrong time and killing the amount of energy you have in that system. So, you know, lots of, so these are just little ways of thinking about it, okay, that, you know, apparently is what some people were searching. Einstein was searching for a kind of an answer, and he was still thinking of a photon as a thing, okay, a thing called a photon, and trying to make it interact with single electrons. And, you know, that model is fundamentally broken, and that's why, in my opinion, you couldn't get that train of thought out of the station. So he spent 50 years not improving his understanding because that model won't work. I mean, it's not accurate. So you can't build anything out of it, or not much out of it anyway. Alright, so I'll take a pause and think about the next direction. Alright, back. Alright, so many subjects, and it's all really, so much physics was done in Einstein's era where you know, a lot of the new modern techniques, all these ways of doing experiments, you know, there's a real revolution, you know, in terms of technology, and so lots of new information, and a real opportunity to start putting these pieces together in physics. And I would just argue that physics made a lot of bad choices, decisions. In terms of what they established as facts, their model of the atoms, all kinds of things they decided that were, in my opinion, just critical mistakes that just, you know, there was no coming back from those mistakes. All right, so one of the things that Einstein that was the cause of Einstein's reasoning, the reason why he went in the direction he went, was the simple kind of Faraday argument that you have a magnet, and you move it into a coil of wire. So if you're thinking that the magnet's doing the radiating, that it has the energy, okay, and that the coil is just an irrelevant object, sort of the argument is that it would be the motion of the magnet, okay, is increasing, okay, the speed of this force, and it's that's causing the effect in the wire, and that you shouldn't be able to take the wire and move it into the energy and get the same effect, because the energy has to be increasing because you're moving the magnet. You can't increase the energy by moving into the field or something like that. I don't really understand why Einstein found this so fascinating, but this is why there's relativity theory. It's essentially because he's saying the fact that it doesn't matter has to do with the fact that the velocity doesn't matter, that the motion nothing has to have energy because it's just relative positions, something like that. Again, it's hard for me to explain it just because my brain wouldn't go that way. My brain would just see the obvious, that what's really happening is there's an interaction between the stuff that's coming off the magnet and the other stuff, and when you're bringing it closer at a speed, you're changing this stuff. And that's all that really is. The motion of the magnet, this field is just doing the same thing it would have done if you just left it still. It's obviously the fact that you're pushing it in just means you're getting it to the surface quicker. How else to say that? Well, we won't worry about it, and we'll just move on to the fact that this relativity thing then ends up being, in general relativity, ends up being an equivalency principle. So he takes it a step further, all right, in terms of saying that, falling in gravity is the same as being accelerated in space. And in a sense, they're really not, because the forces are completely different. When you're being pushed, it's completely different. You being pushed back by the Earth is completely different than you being pushed by gravity. So anytime gravity moves you, you don't feel it. That's the big difference. You never feel gravity, because gravity is moving every little tiny bit all the same. So all the atoms, all the electrons and protons are moving the same. So you can sort of understand that, you have nerves in your body, that are sensing or trying to sense differences. So it's saying this point is the same as this point, the nerve doesn't do anything. When something happens to this that doesn't happen to this, this is going that way, well, then the nerve says something happened. So your body can't feel something changing if everything's changing the same. And gravity always does that. So it doesn't matter how big a tug of war of gravity you were in, you wouldn't feel any of it. So gravity could be, can't really literally be tearing you apart because it's gradual. But the fact is you never feel gravity. So every time gravity moves you somewhere or accelerates you, you can't tell the difference between being accelerated and not being accelerated, because gravity moves all of you at once. And every other force that you would talk about, hitting something, it moves you irregularly, moves parts of your body more than other parts of your body, so you feel every bit of it, because there's a great deal of having to communicate the force through all of the objects. So it's the force comes from the outside, it pushes on this part and it has to move all of these other parts, but gravity moves them all at the same time. So that's a key thought, perception, where now I don't need to create some notion of perfect equivalence, because there really isn't any. And that leads to the light clock, okay, which is another piece of the puzzle. So we'll do that. All right. So through what you sort of get out of looking at Einstein's life is that there were periods where he was focused on a subject, and then he would focus on something else, and then he'd focus on something else. And you're always trying to find something you can grab a hold of and do something constructive with. And maybe that was to his detriment, in the sense that he needed to put in just a little more work on something, and maybe he would have gotten somewhere and completed that thought or that idea. So I would say that in overview, I mean, Einstein had a nice position in life, but I don't think he was very satisfied with what he was doing with that position. That there was a lot of unanswered questions and a lot of incomplete modeling. I mean, this wasn't a finished, it wasn't a well-engineered machine that he had created or was participating in the creation of. And I don't think he was very satisfied with the answers, the spooky action answers. So the light clock is another thought experiment he used, and it's just the way he used it, I think, was a mistake, and he could have realized that, what kind of comes out of it, obviously. And again, it's still making the argument somehow there's a great mystery in the fact that the force would stay the same speed, that it doesn't really interact and gain or lose speed based on how it hits something. That it's, the idea of a constant the idea of a force having a constant speed, and again, I could just make the argument that it has that constant speed because its interactions are really with forces. Forces are only really hitting forces that are moving the speed of light. It doesn't really interact with something moving slower. It's just really interacting with the other force, that the matter, okay? So it's force against matter against force, and the idea is that what it really is force against force. So every interaction with a force is always at the speed of light, is always the same interaction. And that's an idea that just didn't occur to him. All right, so the light clock. So you're moving your vessel that you're in very fast, and the idea is you send photon across the sides of the ship, and what happens to it? Well, there's this idea, okay, that the ship's moving, the side of the ship's moving. So obviously, if you were to look at the photon, okay, and you were moving with the ship, you would see the photon do this. All right, and you could, okay, say that this is the velocity of the photon. This is the path it's taking at the speed of light. But the fact is, it's not taking that path at the speed of light. Okay, so what this does is gives you an excuse. You could have the light travel this path at the speed of light, or you could understand that what the light's really doing is traveling this path. Okay, I mean it's being pushed in this direction. It's apparently moving in this direction. It isn't moving in that direction, right? The side of the ship is moving in this direction. So the photon actually isn't doing anything in this direction. It has no motion in this direction. It's not part of its reality. The ship's just moving away. So the photon's just doing this. It's just going straight across. And it hits this side, not at the time it takes to travel this line. It hits the side at the time it travels this line. Okay, so you don't have this idea of time dilation. So this is the model they use to create time dilation. They just, you want to know how much something's dilated, you just calculate how much longer this line is. So how fast you're going makes this triangle a bigger triangle, right? And that tells you how much dilation you have. You could just do the area of this triangle and it will tell you how much time dilation there is. Now, the interesting thing is this thought experiment fits in with Eddington and the whole photons are bent by gravity argument, because this is where he got it from. And so to figure out how much bending there would be, it's sort of related to this argument about how fast you'd have to go to create this amount of bending. And so that's where he got the 2 times. Photons are twice as affected by gravity, because he needed more bending. So it's kind of so it's another part of the mystique, is the fact that experiment was never repeated with superior technology. And I've repeatedly made the point that the superior technology isn't a little bit superior, it's insanely superior. It's 400 times better resolution from space. 400 times better resolution from space. And they never tried the experiment. We're supposed to believe they never even tried it. You don't need an eclipse. GoPro camera could do it. And they never even put a little telescope on a space shuttle or a space station. You just point it for 10 minutes, So it seems pretty unrealistic that it didn't occur to anybody to. And again, this is one of the things that made Einstein famous, was he made this bold prediction, and the prediction was proven, quote unquote. And so he got a lot of credibility because of that. But what if that didn't ever happen? What if that's not the truth? Nobody wants to ask that question. So anyway, so obviously, in a sense, this thought experiment should have given him an answer about the equivalency principle. This idea that physics is always in a frame. It's always in some little. I could just take a little frame, and I can say the physics in this frame is always the same. I can make the physics of the frame bigger, and I can say the physics in this frame is always the same. And all these frames are all the same, and even if they're on top of each other, and you got frames that are, somehow the physics is always the same. And yes, the physics is always the same, but you certainly can understand you're not going to undo things. So, people go as far as to say there's two simultaneous events in space, and they'll say, two things blow up at exactly the same time. And because your position is skewed and you're closer to one than you are the other, because the light takes time to get to you, you can pretend they aren't simultaneous anymore. They didn't happen at the same time, when of course you're just finding out about them, later. You haven't changed when they happened at all. And you don't change how they affected the rest of the universe when they did explode. You can't change any of those facts. So why are we pretending you can have different times in different places? You can't have different times in different places. But anyway, so this light clock sort of proves the point, in the sense that if you could move at these very fast speeds, what you would see if the photons were able to do this. The other problem is understanding what a photon is. A photon's in a sequence of events. Okay, you can't see down there. It's a sequence of events. Okay, a photon is made of pieces. Okay, that's the frequency. And they have to hit a surface in a way where, in a sense, they're polarized. So they're hitting the surface, bang, 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 bang. And that's how they're pushing an electron. So a single electron isn't interacting with a photon. A photon is a gigantic object when you consider its polarization. It's really large. And it has to hit the surface multiple times to push an electron. And when it pushes the electron, it's doing the same thing electricity does, which is move an electron from atom to atom. And if you put enough energy in, you can push the electron right out of the crystal or the surface. And it all makes sense in terms of understanding it that way. So a photon, you couldn't really throw a photon at a surface and have an expectation that it's going to hit the surface on continuous atoms. So the faster you're moving the material, the photon can't hit atoms that are next to each other anymore, and it can't put the energy into an electron to change it. So in a sense, you couldn't even make one of these light clocks, because almost any substantial velocity is going to destroy the capacity of the photon to interact with the right atoms in the right sequence, at the right timing, at the right resonant frequency of the atoms, to even make a photon detectable. We only detect photons because they make electricity. That's it. There's really kind of no other way to detect them. Our eyes doing that. Any way we measure the momentum of photons, or the energy of photons, we're measuring how much electricity they produce. Anyway, continuing. So what would really happen in this spaceship, if you actually were able to do this experiment and get a thing up to speed, and the photon was able to still be collected correctly, you had some way to compensate for the fact that you're breaking the surface essentially that it's landing on, is that you'd see the photon just kind of like a speedometer. It would just tell you how fast you're going, because you would just keep hitting the other surface. You'd hit the surface lower and lower on the other side. So you'd go from a place where you know where it's going to hit, and as you increase your speed, it hits lower and lower and lower on the surface of the ship, and you could just use that as a speedometer. You could see that it was you who's moving, because it's your frame. Okay, that's all there is your frame, and you would be able to detect it, without looking out the window. You could see how fast you were going, because the photon is an absolute object. It's in the absolute space, moving in absolute speed, a constant absolute speed. So again, that's where I'd say there was a great contradiction in Einstein's reasoning, is that he sort of understood the absoluteness of the photon, and yet was creating a non-absolute space for it to be flying through, which to me doesn't make much sense at all. But again, he was breaking, it was all mathematical, so the idea of breaking time could make this make sense, because all I have to do is change what time is doing to make excuses for photons traveling paths they didn't really travel. Okay. Alright, that's probably enough of that. Alright. Alright, a bit on photons and interference. That was kind of a key thing for Einstein. So he's basically arguing or defending a corpuscle kind of theory of, I have that word here somewhere, there it is, corpuscular. Okay, the Newtonian kind of notion of what a photon is. And that's sort of what he defended in both Brownian motion and the photoelectric effect, where basically kind of, there's junk bouncing around and hitting stuff, and that's why you have an effect. So the photon was kind of understood as that it either did move an electron or it didn't. There was no half moving. There was all of that kind of stuff built into this understanding of what a photon was. And but it was the interference thing, okay, that was the real sticking point. So I think he did, spend years contemplating and trying to come up with some way that he could make interference compatible with a more mechanical, it's just a photon is a thing, it moves through space. Photons don't interact with photons. So the idea of some slit experiment, okay, and it was sort of well demonstrated. Okay, so Einstein is before laser beams. He's before a lot of technology. To do two slit experiments, they really had to do a regular light bulb, produce light, goes through one slit, and then you have to put it through the two slits, and you get a fuzzy pattern, blah, blah, blah. It wasn't great technology. So the idea that it happened, that you had these stupid fringes, and again, now it's based on the idea too. I mean, how much did Einstein know about the real double slit experiment, in the sense of not doing what they, the math dictates, which is have infinitesimally small slits or infinitesimally small impediments, and thereby essentially eliminate what is the experiment, which is the idea that you have point sources, you have surfaces. So it seems clear that Einstein didn't understand the slit experiments as surface experiments. That it's really just about what Newton demonstrated by doing the two experiments, shooting light through an opening and then shooting light in against an impediment. And really what you have is surface experiments. There's two surfaces. The two surfaces are essentially doing the same thing, whether they're pointing out or pointing in doesn't make any difference. And that's why you get the same pattern, basically, essentially, with a difference in the brightness of the center. But otherwise you get the same pattern because it's just about the surfaces. And so the two slit experiment is really the four surface experiment, which means it's really the 4 point source experiment. And you could sort of understand that if I make any point sources too close to each other, I can't possibly have any difference in the length of the lines from them to any point. So I can't make a difference, a wavelength of difference, if these 2 point sources are so close to each other that they're indistinguishable. I can't make a path length difference. I can't make a wavelength of difference between the two lines. And so in a sense, I've just destroyed a 4-source experiment and turned it into a 2-source experiment. So so the basic Jungian model wasn't really the double slit model. It was the model of changing the double slit into the single slit. I mean, back into a single 2-surface experiment. You're taking a 4-surface experiment, turning it back into a 2-surface experiment, because you're making 2 of the surfaces so close that they're out of the experiment. They don't exist as 2 surfaces anymore. 2 distinct surfaces, or 2 distinct locations. So how much of that he understood, that's, who knows. And, because the real pattern, again, has the 2 patterns in it, okay? It's, I shouldn't have to draw it. I've drawn it so many times. I mean, you could have 5 objects here, and then there'd be 3 or 4 here, and then 3 or 4 here, and you have these glaring empty spots. Okay, so you essentially have 2 patterns. And the simple argument is in the double slit, the reason why you have those 2 patterns is because you have point sources that are really far apart here. So these point sources, obviously these 2 points are really far apart, meaning they can have lots of path differences. So they'll make lots of little nodes. So the further away the 2 point sources are, the more locations where you have a wavelength of difference. And the closer they are, so the 2 closest surfaces would be making gigantically big nodes of, where the line, there'll be much fewer points you could go to where you'd have a wavelength of difference. And these get bigger as you go here, so they get smaller. There's also all kinds of little rules that nobody knew anything about because they were all using this Young model, which basically destroyed the 2-slit experiment and converted it back into a single-slit experiment. But that's why there's 2 patterns, is because you're really saying when are the 4 sources in alignment, and that's where you get a spot, and you get a spot, and then you get a spot, and then you get a spot. So what you're seeing is where all 4 sources are in phase. Not only the sources here, but the sources here. So all 4 sources are in the same phase, which means the photon they're all in alignment. They're hitting with the same rate. They're hitting at the right rate to create a photon. And so all those locations are getting hit with the same amount of stuff. It's just when it's in phase and when it's out of phase, something like that. Okay, I don't even know if you can see, can't even see that. It doesn't really matter. Phase should be understood, and how simple it is. You're just changing the phase, you change the phase, you change the interaction, you change whether or not it triggers the addition of energy versus the destruction of the energy. So it's really about breaking and making photons. So this is what Einstein needed, was a theory of a photon that understood that it's a sequence of events, and that all you're really doing is saying that you can take out an element of that sequence of events and put it in the wrong location, and now you have a broken phase. You've now destroyed the sequence of events that are going to cause the effect. You've taken a piece of the sequence out, and that simply you could just replace that piece with another piece from another location. So what you're really saying is that I'm breaking photons on this surface, I'm breaking the photons on this surface, and the fact is I'm sending pieces to both this location, and the pieces are just going to be, one surface is going to send this bit, and the other surface will send these 2 bits, and I'll end up back with 3 bits at the right frequency. And that's all you're really doing, is reconstructing a photon you broke. So that's the trick Einstein needed. Was first he needed to understand that photons are composite objects, and I don't know if he did that. I mean, everybody was drawing a photon as some sort of, here's an electron, it interacts with something, and a photon flies off. So everybody was thinking of an atom, a single atom, and they were thinking that a photon just flew out of the atom. So a single atom could make a photon. And I think it can really be understood that a single atom can't make a photon all by itself. It needs other atoms to also provide the elemental pieces of the photon. And that, might be 3 atoms, might be 10 atoms, might be 50 atoms. If you understand that the wavelength is, the wavelength of a photon, a 500 nanometer photon, that's 1,000 atoms. So you could fit 1,000 atoms in the wavelength of a photon. So their frequency is gigantic, but you could also understand that the polarization of electromagnetic radiation is proportional to the frequency. So if it's 500 nanometers of frequency, then it's probably 500 or plus, or minus a little nanometers of polarization. So you're saying the photon is flying through space with a polarization that is thousands of atoms across. How could that object interact with a single electron? How could it interact with a single atom? It's thousands of atoms in size. How could it possibly interact with a single atom? So that kind of reasoning, I guess, wasn't included in Einstein's understanding. And so it wasn't as easy for him to say. It was easy enough for him to say what I said 10 years ago, which is there's no way the photon is splitting into 2 objects and the 2 objects go through the slits and then somehow interact with each other in space. Because he did know that photons don't hit photons. And going through a slit isn't going to make a photon into some hittable object. that even if I put photons through a slit, a flashlight, any kind of thing, and I put it through some object that has a slit in it, I'm still not going to get the photons to interact with each other. And so the whole idea that the event happens here in space, the interaction, I think he dismissed that as, that's not plausible. He knew the event happened here, okay? The event is happening at the surface. The surface is the obstruction, the interactor, the thing you're interacting with the photon. The event happened there, and that event dictated the byproduct. Okay, there was no interaction necessary in space. And so I think that was the conflict he was trying to resolve, and he just wasn't successful. And it's just a matter of, if he had a little more. I mean, it's all about what time you're born and how you're, when, blah, blah, blah. All these arguments have to happen in a sequence, and that's a real problem with science. Science doesn't take on these subjects one at a time. It's taking them all on in different periods of time, and people, it's like Mendel with his peas. Darwin never read it. It's a huge piece of context sitting there 20 years, and the right people didn't know about it. So those kind of things, those circumstances are kind of decisive to, how this whole argument progresses, and the fact that science doesn't say, let's for the next 3 years all the scientists work on one subject. They're all working on different subjects in different places at different times, and none of it is like, there's no special place you go to discuss photons. There's no place to go to discuss relativity. There's no, there's just nothing that coalesces all the arguments and says what are all the facts we have and what can we do with them. Because if Einstein did have a little bit more knowledge about what the two-slit experiment actually was, that it was these two patterns, like I said, I don't know for sure he knew that there was an envelope pattern. Because it's sort of a giveaway. It sort of is telling you something, in terms of why are there two patterns, and it's sort of telling you, well, because there's two openings. That's one explanation. But the better explanation is that there's two, completely different phenomenon. Very large distances between two surfaces and very small distances between two surfaces, which really gives it away that it's a surface phenomenon. So like I said, 10 years ago I couldn't argue this very well because I didn't have all these little pieces of the puzzle. But once you have them, it just becomes sort of obvious that this is all about surfaces. All the fringes are created by photons that go by a surface. The ones that don't go by the surface just plow straight through and are unaffected. So it's nothing like the Feynman argument. There's no randomizer, that any photon that goes through the slit, it gets randomized. None of that happens. Anyway, alright, that might be enough of a video. And so I will come back to this and try to be a little more, putting it together better. There's just, but there is a certain, in reading it, so the book is really bad just because the book is always jumping between time periods. So it doesn't have any, like I said, there's no chronology of Einstein's reasoning. But the fact that all these subjects there are connected bits between the subjects, and it is just kind of ironic, I just say, that on the relativity idea, Einstein is very anti-materialistic particle, and then on the photon energy idea, he's very particle, which is just kind of strange that he was able to argue for both of those positions. Because from my point of view, he also had the notion that the whole thing would be one thing, that there is one answer, one key that fits all of the, there's a skeleton key, there's a simple answer that unlocks all the locks, so it just, it is kind of hard to understand hard for me to understand how he could find relativity compatible with his, pretty aggressive belief in corpuscular energy. But anyway, it is thought-provoking. So these are the thoughts it provoked. So till the next time, such and so forth and whatnot. Do this part. This has been at draftphysics.com. Debatephysics.com, which I would really like to do some debating, but I can't find anyone willing to defend wave theory or relativity or the state of the evidence or any of that. So, till the next time and such.